Okay, thanks everyone for coming to the final UF Physical Mathematics seminar of the semester. We're really happy to have Yi-Hsien Du from MIT. She's going to tell us a bit about nonlinear bosonization of non-Fermi layers. So whenever you're ready.
Yeah, thanks, Robert, for a nice introduction and giving me this opportunity to speak here at this wonderful environment of CMSA Harvard University. So today I'm going to tell you about the work we have done on this topic of nonlinear bosonization of Fermi and non-Fermi liquid. Okay, so firstly, I would like to tell you what this talk is about and why this subject is so excited. So the main system that we will be focusing on is a system with the Fermi surface. So what we're going to do is that we want to write down the bosonized nonlinear or linear effective field theory action to describe the system with the Fermi surfaces. And we know that this kind of, for example, the conventional method or the Fermi liquid problem is usually introduced by the great physicist Lev Landau back to 90s. However, in the old studies of this Landau's Fermi liquid theory, it's not a field theory description. So this gives us a motivation why we want to write down the bosonized nonlinear field theory. Okay, and there are many approaches that we can write on this effective field theory. But one thing I want to emphasize today is that by using this so-called coherent state path integral formalism. So now we can ask why this topic give us some benefit to study more about this. Well, I would say that this gives us a motivation and benefit to study the linear and non-linear responses. So for example, in the illustration here, you can see if we want to compute some higher point correlation function, for example, like the 3-point density correlation function, and in the fermionic side, that people usually use the one loop diagram to compute those correlation function. But in our approach, we can see we match we actually only need the tree level diagram to compute those nonlinear response. So you can tell that this gives you a dramatic reduction of the calculation length. Let's give us some flavor of how much calculation is reduced. So for example, like this can be lengthy for like 50 pages, but amazingly, we find out that the reduction, after some reduction, that the computation will be going down to like 2 pages. So our technique, there's something I want to highlight is that it provides us this benefit of computing this nonlinear responses. So it will be give us some benefits when we want to study, for example, the non-Fermi liquid problem. Although we will be focusing on the Fermi liquid problem here, but we will have some goal that in the future that for understanding on conventional methods, there's some loop diagrams that can be dramatic reduce the calculation, and we might be able to understand those problems much better. Okay, so what is the system that we want to understand today? Well, I would say it's a system with a Fermi surface. So if we can do now that we do some thought experiment and consider this a box. And now what we're going to do is that we want to throw some fermion into this box and how to describe the state of the system. So the state of the system can be described as some wave function. Now what we're going to do is that we add more and more fermion into this box. And by the thermodynamic limit, we know the system will form the system with the Fermi surface. like what we illustrate here. So the system that the physical system that will be studied will be the gapless spaces with this Fermi surface. So for example, we can study Fermi and non-Fermi liquid. So what are the examples? For example, not only the conventional metals, we can think about hot-filled Landau level with some finite density with short-range interaction. Okay, so this is the system we want to discuss today. So now we can ask, what are the access to this Fermi liquid problem? Well, ranging from condensed matter systems to high energy and astrophysical systems that can access to this Fermi liquid problem. So for example, that in the condensed matter system, there are something like the conventional metal, or even the liquid helium-3. And in the high energy and astrophysical systems, systems like neutron stars and white dwarf. Although we will be focusing on the condensed matter system, especially be focusing on the conventional metal due to the time limited. But I want to emphasize that actually this formalism we will talk about today will also give us some benefit to understand better of this high energy and astrophysical systems. Okay, so as we mentioned previously, that this kind of Fermi liquid problem have been understood by this great guy, Landau, back to 90s. So there's a theory called Landau's Fermi liquid theory. So what is Landau's Fermi liquid theory? Well, it's a theory of Landau's quasi-particles. And we know that actually the Landau's Fermi liquid theory is not a field theory description. So what do we mean by that? Actually, there's some, for example, the kinetic equation that we can find out in this kind of, in this Landau's Fermi liquid theory. And in there, something I want to emphasize, because we will be also talking about later on by using two other different approaches, is to compute, one can compute that the linear and non-linear responses from this kinetic equation. But in this Landau's Fermi liquid theory, we know this all this computation will be only up to the leading order in momentum. So what's the goal today? Is that we need to go beyond this and find out a field theory description of the Fermi liquid problem. And something I want to emphasize that this goal might give us some benefits to understand beyond the Fermi liquid theory. For example, that when we study the problem of non-Fermi liquid, that this field theory description might be very helpful. Okay, so I've been telling you that the system we were discussing is that the system with this Fermi surface. And I also tell you that there's a Landau's Fermi liquid theory to describe this kind of system to understand the conventional metal. So the goal that we want to do is that we want to write up a local effective field theory for the Fermi liquid systems in some bosonic degree of freedom. So what is effective field theory? Well, this gives us some description of what it is. So effective field theory is the description of physics of a system on a particular energy and depth scale based on general principles. Okay. So now I'm going to tell you how can we treat this kind of liquid theory and describe it as the droplet evolution. Okay. So one can ask, when we talk about the Fermi liquid, what is the state of the Fermi liquid? We'll here give you some illustration. How can we think about the state of the Fermi liquid? It's described by a closed Fermi surface in phase space with some arbitrary shape and volume. And here we give you some examples. How can we visualize the state of the Fermi liquid? So we know that this Fermi liquid lives in phase space. And this phase space, if we quantize it, you can view it as the non-commutative space. And one naturally can arise that we can think about this kind of problem as a droplet, which lives on non-commutative space. Because we have been talking about mentioning the words non-commutativity. So one can introduce is that what is the non-commutative field theory? So well, the non-commutative field theory is that the quantum field theory and lives on non-commutative space. You can see here that the coordinate is non-commute and be related to this data called the non-commutative parameter. We can view it as the H bar in quantum mechanics. So there are two very important properties in this non-commutative field theory. One is that one can define the two functions by this Moya product. As you can see, it's defined like this. And by using this Moya product, one can also find out there's a this Moya, so something called Moya bracket, due to the definition of the Moya product. And there's one interesting property that we'll be using in today's talk is that actually this Moya product can be understood by some expansion of this non-commutative parameter up to some order, higher order. And if we keep track of this order of the non-commutative parameter, in the leading order, actually the Moya bracket, you can see here, will become the Poisson bracket up to only the leading order in non-commutative parameter. So please keep in mind because I will be using this property later on. Okay, so why non-commutativity is so interesting? So first of all, it provides a systemic formalism to the quantum field theory action of this Fermi liquid theory system. And it might give us a new perspective of this nonlinear bosonization. And also from there, we can find out the quantum version of the algebra. And because that when we talk about non-commutativity, due to uncertainty principle, we know we can reach out some vastness property of this Fermi surface systems. And also, we can find out the analytic correction due to this non-commutativity. Okay, so I've been telling you we can thinking about this droplet and living in non-commutative space. But let us going down to some semi-classical limit of the whole systems. So in the semi-classical limit, the whole system, you can think about there's some droplet and in the phase space. Okay. So now we can ask a question. How can we describe that the system and with some under some time evolution? How can we describe the time evolution of the system? Well, so the time evolution is actually governed by the kinetic equation in the semi-classical approximation. And as you can see here, the visualized point of view is that actually initially you can find out some, there's some droplet configuration initially. So for example, in the initial condition, you can choose some spherical and translation invariant simple connected original configuration. And later on, under some time evolution, this kind of droplet system will start to change in its shape. So this equation of motion is governed by this kinetic equation. And how to think about this? Actually, if we think about one single particle and living in phase space, we know the time evolution of this single particle is described by some Hamiltonian evolution. So this kind of system can be thinking about as a group of particles. And we think about time evolution of this group of particles of some fixed density or in the domain, and describe this by the canonical transformation. So actually, this kind of time evolution of the droplet, there's some dynamic of the droplet. And something I want to emphasize in is that there is some volume preserving of the phase space volume, because that we will have the particle number to be conserved, so that the volume that includes by this Fermi surface, which is defined by the phase space integral of some distribution function, is that this phase space volume under the time evolution will actually be fixed. And there's one important property that there's some distribution function inside the Fermi surface is 1, and outside of that is 0. And this condition will be preserved on the time evolution. Okay, so I have been telling you that what is the time evolution of the system? And it's governed by the semi-classical limit of this kinetic equation. So let me emphasize it again that this kind of Fermi liquid system can be described. This droplet can be described by some phase space distribution function. And it has some properties that inside of that is 1, and outside of the Fermi surface is 0. So if we don't go to the semi-classical limit, actually the time evolution of this is governed by the this constant kinetic equation. And you can see this bracket is related to the Moya bracket that we've been talking about in the non-commutative field theory. And we had been emphasizing that there's one important property that the Moya bracket will be reduced to that the Poisson bracket in the leading order of the data. So which means that naturally arises that in the semi-classical limit, it will becomes that the normal kinetic equation that we've been familiar with. Okay, so which means that in the semi-classical approximation, we can define this droplet shape and thinking about the dynamic of that. Because we don't talk about uncertainty principle, so the droplet shape is well defined, and we can thinking about some evolution of this droplet shape. So if we zoom in to that, the kinetic equation, because the kinetic equation is related to the phase space Poisson bracket. If we zoom in more to that, we find out that actually the kinetic equation is just that the Lagrange equation of the three fermions. And under this time evolution, the initial condition that F0 outside of the Fermi surface and inside is 1, this condition will be preserved under time evolution. So what can we use this kinetic theory to compute something? So I want to emphasizing on computing the linear and non-linear responses due to we will also use 2 other approaches to compute this linear and non-linear response later on. So now if we expand the fluctuation of the distribution function in terms of the background field A0. So we know that the kinetic theory can be written down like this. And by computing, we know that, for example, we can compute the density 2-point correlation function. Or we can also obtain the nonlinear response, the 3-point density nonlinear response in this regime. And keep in mind this property, because later on, we will find out that by using the formalism we developed, this will going back to this result derived in kinetic theory. Okay. So I have been telling you that we are considering the system with the Fermi surface and talking about the time evolution of the system with this Fermi surface is governed by some kinetic theory. And we use that, the kinetic theory, for example, you can compute the linear and nonlinear responses. And for the next step, what we're going to do is that we'll build up the bosonization through this approach called coherent state path integral. So before I jump into the coherent state path integral, let me going back and tell you about what the previous work people have been doing great work on building up the effective field theory for Fermi liquid. So for example, that's there's a Landau Fermi liquid theory can be written as the effective field theory of fermions. And in those work that we know that Fermi surface can be divided into patches. So there's some thing we can thinking about, because in naturally arise, there's some unnatural cancellation between the diagrams in perturbation theory. And because we're aware of this unnatural cancellation of the diagram, that's give us a motivation why we want to study bosonization. So for example, in 1+1 dimension, that the fermion is due to boson. And one natural question to ask, what about we want to generalize this description to a higher dimensional bosonization? So people have been thinking about this. And in that kind of work that we're thinking about, there's some chiral bosons at each point on the Fermi surface, because we have the patch theory. So the visualize, how can we thinking about this kind of problem is, for example, we have a 2-dimensional system like the figure here. And what people have been doing is trying to decompose it to the infinitesimal number of 1 + 1 dimensional system. And in each of the 1 + 1 dimensional system, there are some chiral bosons at each point of the Fermi surface. Okay. So one can ask a question: what is the general rules for formulating the effective field theory action? Okay, here comes the formalism. How can we formulate in this theory? So this is the something called the coherent state approach. We can think about the coherent state as some deformation of the droplet here. So firstly, we want to thinking about there's some fermion bilinear or the particle pair, and we're thinking about that as some generator, like we define here in terms of phase space parameter. So the coherent state can be defined by using this fermion bilinear. As you can see, it defined like this. Okay, so now we can take the step of doing the semi-classical limit, and this will going back to our work, previous work on this topic of the coadjoint orbit. So if we want to take a semi-classical approximation, and actually there's some algebra that we need to be aware of. For example, if you define some operator, and this f is an arbitrary function of the phase space, and this O here is just the fermion bilinear that we defined previously. And we talk about there's some algebra of two operators here, and you satisfy by related by this Poisson bracket. So this is actually the Poisson algebra, or it has another name called this W infinity algebra in the semi-classical limit. Okay, so I've been telling you in the semi-classical limit, this formalism will be related with this coadjoint orbit approach. So how can we be hand-waving talk about this coadjoint orbit? Well, this coadjoint orbit will we can understand they give us the space of the possible Fermi surface state. Actually, by choosing the initial configuration of one possible Fermi surface state, and we can thinking about all the possible canonical transformation. So all the allowed state is described by this coadjoint orbit obtained by the group of canonical transformation. So we can thinking about there's some dynamic of the droplet which occurs on coadjoint orbit. And if Fermi surface state or the droplet configuration, because we've been talking that each state of the Fermi liquid is correspond to configuration of the droplet. So each of the Fermi surface state is a point on this coadjoint orbit. Okay. So we have been using this coherent state approach and talking about that the semi-classical limit will going back to the work of this coadjoint orbit description. But let us jump back to the coherent state interpretation of this Fermi surfaces. So what is a state? So the state is the expectation value of this fermion bilinear. And we can find out the ground state and actually the state by the expectation value of this fermion bilinear. And we know that the ground state and the state can be related by this parametrization here and related with the Moya product. And in this kind of systems that this kind of description, there's actually some redundancy. If you choose some other parameterization, and this will give us the ground state hitting on that and leading to the same ground state. So we know that the space of the state can be thinking about as some coset. One can reduce this redundancy by choosing gauge fixing condition. And the gauge fixing condition that we choose is actually we fix the magnitude of the momentum, and only thinking about that the theta dependency. So we can now relate it this phi, bosonic phi, as a scalar field which lives on the Fermi surface, and it only depends on the angular part. But actually, one can choose other gauge fixing condition as well. But then maybe choosing this in this talk. Okay. And again, that in the semi-classical approximation, one can define the ground state like this, and so the state can be related as well. So here comes the main conclusion. How can we write down the effective field free action of this coherent state half integral approach? This is the effective field free action that we can write. It contains two parts. And the first part with the pi derivative here is the Wassel-Wiener term. And we can thinking about it as some Barry phase term, which characterizes the state carried adiabatically around the path in the coset space. And the physical point of view of this first term is that, for example, we talk about this droplet configuration, changing the shape. And we know that under the shape changing, that you'll pick up a adiabatic phase, which is related to the Barry phase. And it's a universal and fixed term. You can find out in this Fermi liquid theory. And the second term here comes with the Hamiltonian term. And it's defined by this formalism here. But we know that we are doing an effective field theory, so one can also write down other terms. For example, sweeping on interaction due to some Wilsonian coefficient, but it's hidden in this ... term here. So I've been telling you that we use the coherent state half integral approach and arise this action contains two parts of the Wassel-Wiener and the Hamiltonian term. Okay, so previously I showed you how we build up the effective field theory action by using the path integral coherent state approach. And in the semi-classical limit will be related with the coadjoint orbit approach and show you what the formalism of the effective field theory action will look like. But I didn't show you is that what's explicitly how it will look like. And in this section, I will be zooming in to the effective field theory action, but in the semi-classical approximation. So if we find out that the Gaussian theory, which means that up to the projective level of phi, so we know that this will just recovers or the previous multidimensional bosonization result. And also the density operator and the 2-point correlation function will just match all the previous result. And we know that because it's a patch theory, there's nothing that when find out that the nearby boson will actually talk to each other. So we know that there's a chiral bosons based on Fermi surfaces in this Gaussian theory we can think about. And here comes the main part that I want to emphasize, which is the nonlinear effective field theory. So one can ask, what is the nonlinearities will comes from this result? Actually, it contains 2 parts. The first part is the geometry of the Fermi surface. So we can see here for the Weissman-Norwegian term part. So the nonlinearities will come from the this, for example, the 1 over Pf, and Pf is the Fermi momentum, and this is related to the Fermi surface curvature. And we also have this term here, where n theta is the unit vector along the radial direction of the Fermi surface. And the derivative with respect to theta of this unit vector is actually related to the extrinsic curvature. And that's also one kind of term that I want to emphasize. You can see here, there's a derivative of theta of phi. So this tells us that actually the nearby boson will talk to each other through this kind of term. Okay. And the second part is related to the Hamiltonian part. You can see here, this is the dispersion relation up to some derivative with respect to momentum. And we find out if we want to have the nonlinearities, we have to have the dispersion to be nonlinear. Okay. So here gives us some flavor how these nonlinearities will jump in. And I want to tell you why this nonlinearity can give us some benefit of using this formalism. If you still record that in the first chapter that we've been talking about, we can use the kinetic theory to compute the linear and nonlinear response. And we can also do here. So in the fermionic language of this system, if we want to compute, for example, the 3-point correlation function of density, and in the fermionic side, we know we want to compute the one-loop diagram in the fermionic side. Amazingly, we find out that this will match in our approach, bosonized approach. This will match to only the tree-level diagram. And I want to emphasize that the exact matching is actually non-trivial. So this also matches to the density 3-point function from the kinetic theory that I've been telling you previously. Okay. So the thing is that we have the fermionic side of this nonlinear response, and which match to the formalism we can compute today of this tree-level diagram, and also from the kinetic theory. So all different, 3 different approach on the result will match to each other. And from our calculation, this will reduce the calculation dramatically. And because this is a multidimensional bosonization up to some arbitrary dimension, So one natural question to ask, what about 1 + 1 dimension? So in the 1 + 1 dimension, one can also check this related with the Lottinger liquid action or trichiral bosons. Okay, so I have been zooming in the semi-classical approximation and telling you what the effective field theory will look like with some bosonic degree of freedom, and tell you what the nonlinearities comes in and leading to the computation benefits of the nonlinear responses. So now what I'm going to do is that I want to switch in on the gauge fields. In the previous studies, we have been focusing on the Fermi liquid theory. So now what we're going to do is that we want to go beyond the Fermi liquid. So how can we couple the theory to the gauge fields? Is by using these gauging procedures. So we can couple the theory to the gauge field of phase space. You can see here's the gauge field of the phase space. And then treating that the gauge transformation as a subgroup of canonical transformation. And we have been telling you that phase space can be thinking about as some non-commutative space. So which means that those gauge fields can be thinking about as the non-commutative gauge fields. Which means that the gauge transformation are non-abelian. But because we want to talk about the physical systems, so there's an open question that one can ask. How can we switch in on the usual electromagnetic field and in the presence of the barrier connection? So this is some open question we can thinking about. Okay, so our formalism will actually give us some tool to something called the LU1 anomaly, and this described by this gentleman here. So the emergent low group symmetry is an emergent low group symmetry or some Tuhu anomaly and coupled to the background fields. So the emergent LU anomaly, as described by those people, are characterized here. So we find out in our approach that we can compute the covariant Wall identity for the canonical transformation in phase space, as we can see here. This is the result. And I want to emphasize that in the linear approximation, our formalism will be related, will be just this emergent LU1 anomaly by the linearized approximation. Okay, so we have been focusing on this Fermi liquid, and now we want to go beyond that. There's some non-Fermi liquid, or we can call it another name of strange metals. So for example, in the experimental side, there's some high TC superconductor, strange metal cuprate. This kind of system is that still have some Fermi surface, but have the thermodynamic and transport property. It's not like the Fermi liquid problem previously. And this is in the experimental side, but if we want to think about some theoretical side, there's some, we can formulate the theory by thinking about the Fermi surface and couple to the gapless critical boson of gauge fields. Okay, so here give you some flavor. How can we build up the beyond this Fermi liquid theory? So for example, this effective field theory action shows you how can we couple the bosonized effective field theory action we built up previously in the arbitrary dimension and couple it to the dynamical gauge fields. So if we're thinking about the critical dynamical exponent z equal to 3 at 3 levels, we can find out that the magnetic field is Landau depth, like we can see here. And one can ask, what about beyond this 3 level? For example, that z is not equal to 3. So one can compute those diagrams, those higher loop diagrams. So as you can still remember, and we say that this nonlinear bosonization formalism, one benefit is that we can reduce the loop calculation dramatically, right? So which means that, for example, this kind of loop diagram can be effectively thinking about some effective vertices. So those computations can be reduced dramatically using our formalism. So the benefits, there's comes another benefit of this formalism for understanding problems beyond the formulate theory. This kind of approach might be very useful for computing those tedious diagrams. Okay. So one can also thinking about what, how about if we can, there's some extension of the algebra. So for example, in the spinful Fermi surface, you can extend the algebra to include those. And also in the BCS theory, we can also include the algebra with all those terms. So that the coherent state with this extended algebra can be formulating by this. And we know that in the semi-classical approximation, the extended algebra, if we define there's some operator like previously, and this will be related with this extended algebra, where this F is the structure factor. Another question one can ask is how can we include the Barry curvature? So there are several different ways that one can include the Barry curvature in this formalism. But let me be emphasizing in one of the way to include the Barry curvature is that actually one can modify the Poisson bracket with the Barry curvature correction in phase space. As you can see here, if you think about the coordinate to be non-commute, it will be related with this Barry curvature. And by using this modified Poisson bracket on the equation of motion, will be governed by some gauge invariant distribution function. And this is the modified equation of motion of the system, where we find out, identify there's something called anomalous velocity. Then another thing that one can compute is that if we compute the nonlinear current responses, and we can, by using the Kubo formula, there's some hole conductivity that one can compute. And this gives us a connection to the anomalous hole effect. So in this session, I have been telling you that if we going beyond the formulate theory, and what is the effective field theory action one can write down, and also I tell you how can one switching on gauge fields, internal phase space, and telling you how to extend it the algebra also. So now let me make the conclusion of this entire talk. So we want to write down the effective field theory action of some system with the Fermi surface. And the approach that we are using is the coherent state path integral approach. So what can this give us? Is that we actually write down the systemic formalism from the nonlinear effective field theory action of Fermi surfaces. And we know that a state of the Fermi surface is the droplet lives on non-commutative space. And we know that the algebra is as some algebra with the Moyal bracket. In the semi-classical limit, it becomes the algebra with the Poisson bracket. So we build out there's a nonlinear bosonization and arbitrary dimensions. And we also compute the linear and nonlinear responses from our approach, and which will reduce the calculation dramatically. And this will be also very useful for the problem beyond Fermi liquid theory when we compute the tedious diagram of the loop diagrams. And there's some wish list. So one can understand the non-Fermi liquid theory more carefully by coupling to the critical bosons of gauge fields. And in the studies, it's mainly focusing on the semi-classical limit. One can ask, what is the Moyal bracket generalization? For example, we can thinking about the 2K physics, BCS problem, or there's some non-analytic fractions. And one can also thinking about non-Fermi liquid plus disorder. And there are more to think about. Thank you.
Thank you for the great talk. Do we have any questions in the room?
So I wonder if gapping out the Fermi surface is corresponding to gapping out the bosonic field.
Sorry, what?
I wonder if gapping out the Fermi surface is corresponding to gapping out the bosonic file.
So what do you mean by
Maybe by formulating some order such as the superconductivity to gap out the Fermi surface. Is that corresponding to the gapping of the bosonic field?
I think that's a very interesting question to thinking about that we didn't do previously. So that's definitely one short-term goal that one can do. Yeah, thank you for the comment.
Any questions over Zoom?
I have a question. So
Yeah.
actually, I missed most of your talk. I just saw my email announcement of the talk and
Yeah.
joined. But I have a question. So were you able to study the after you kind of bosonize or something? Can you study the fermions, or is it sort of like a one-way mapping?
I think okay, great. So actually, if we want to have the full description of this language, I would say that in 1+1 dimensional system, then one can fully having the fermionic language in terms of bosonic language in 1+1 dimension. But in the higher dimensional case, I mean, one needs to be more careful about that. Yeah.
Okay.
Thank you.
Thank you.
Any more questions? No? Well, thanks everyone for coming. I hope to see you all next semester. And let's thank Yi-Hsien again.
Yeah, thank you.
This was a great talk.
Yeah, thank you.